Okay, so I hadn't planned anything too intricate. I just preloaded some problems that seemed fun from the Erickson book. Um, and I'm just going to show them and give you guys some time to look at it and then solve them. Alternatively, if there's other problems that you guys had picked out from the practice problem sheet, I can look at those instead. Yeah.
Are we going to get a copy of the cheat sheet before the exam?
Yes, and you should have. So I will. Yeah, that's been propagated to TAs.
It may have been
Okay, it's awfully similar. I just updated it with uh, whatever running times we've done since midterm one. I kind of elaborate a little bit more on kind of the dynamic programming type instructions, and then, but you guys already saw that on the PSO, except for maybe some typos. And I think I reminded you to write darkly so that the Scantron can do better. Yeah.
Do you expect the exam to be like mostly based on stuff that we covered since one?
No, I think it's probably closer to uniform. Um, yeah. Other questions? Okay, I have office hours today, and I can always answer other questions in other situations. Um, okay, so uh, first, let me tell you what problems I preloaded just in case maybe if you finish early, you can race on to the next one. This one was exercise 11.6. Another one was exercise 3.18, which is dynamic programming one, and another one was exercise 1.26. Okay, I wasn't really sure. Yeah, it's a little awkward, but okay. So, okay, I'm recording. Let me okay, let me then just read the problem out loud so we're all on the same page, and then I'll give you guys some time to work on it, and then I'll just open the floor uh, to gather questions. Okay, so the SPU, okay, computer science department, they're making a mini golf course. Um, so the playing field is, they have some kind of closed polygon bounded by some horizontal and vertical line segments meeting at right angles. And there's already some holes that have been kind of dug in and starting points that have been dug in. And you want to set up a mini golf course, which is to say sort of like you want to, how do they describe it? Okay. Uh, so we only have the locations of the starting points and the holes, but we lost track of which kind of starting points for the mini golf corresponds to which of the holes. Um, Describe and analyze an algorithm to compute a one-to-one correspondence between the starting points and the holes that meet the straight line requirement. So a starting hole or starting point and ending hole, they have to be connected by a straight line that stays in the course. And you have to figure out what they might be, and assume that you can kind of figure out intersections and constant time. So if you have a line, another line, and instead of worrying about the arithmetic of whether they cross, just assume you have some subroutine to figure that out for you. Okay, so I guess the input, an example might be like this picture. So the starting points are the stars, and the ending points are the circles, and you have to draw straight lines to make, I guess, a legal mini golf course. Okay. Does that make sense? Okay. I understand there's maybe a lot of geometric details. I wouldn't worry too much about, just at a high level, how to more or less reduce it to something we've done before. Um, I'll give next 5 minutes. Or is it better if I introduce the other problems first so that other people can work ahead? Or should we stay here? Okay, we'll stay here. Feel free to chat with each other and have fun. Oh, you figured it out?
Well, I figured out that the answer, it's like not a great solution. It's like, I don't think it's.
Okay, yeah, we'll probably wrap up soon, but it seemed like some people were still working on it, so I was giving a little more time. Maybe in a minute I was going to ask if people are roughly ready. It might be good practice to force yourself to write just a little bit. I don't know if you have a. Uh, just a brief show of hands. How many people have finished? Okay, maybe I'll give 90 more or a couple more minutes. Uh, maybe another show of hands. How many are roughly done or ready to discuss? Okay, that seems like most. Okay. All right. So let me. I'll copy this picture over for some context. Okay. So does anyone want to go forth and at least suggesting at a high level their approach? Yeah. Okay. So let me just trying to catch up. I think this is what you described. Okay. I'll use this as an example. Okay, so let's say okay, so let me number these 1, 2, 3, 4. Can you hear me in the back? 5. And the holes 1, 2, 3, 4, 5. Okay, and I guess you said you want to draw an edge whenever there's a straight line that's visible. So I guess if I were to look at number 1 here, it can get to 2 and 3 and to 1, and not really sure if it can get to 5. Okay, so 1 can go to 2, 1 can go to 3, 1 can go to 1. And then if I went on to the second hole, it seems like it can look at number 5 and it can look at number 4. So I would draw an edge to 5 and 4, and so forth. So we're drawing edges. Sorry. We're drawing edges whenever those two things are visible to each other. And okay, so matching, taking an edge corresponds to matching up a starting point with an end hole. Okay, so let me do two things. So one thing you said, when we solved this, we sort of turned this into an edge disjoint path problem. Okay. And we sort of have two different options. We have a couple of different algorithms. We have a strong polynomial time algorithm. We have a Ford-Fulkerson algorithm where running time depends on the size of the flow. So if you had done, okay, so here's always just to be careful. There's a little bit of double checking we have to do because the stories give some m's and n's, and that may be different for the number of vertices and number of edges. So just to be clear, the number of vertices is n. Yeah.
Wait, why didn't you include all of the possible paths in this?
Oh, I think at some point I didn't draw all the purple lines. I just I thought you guys were getting bored, but I would have drawn all of them. Okay, so there's n vertices. Now, one thing maybe not clear is how many edges there are in the graph. Okay, so how would you evaluate the number of edges? Or you want to upper bound it? Yeah. So mn. So I think m is the number of corners of the playing field. So okay, so n squared. So really, the best upper bound we can get based on this story is n squared. Certainly if it was just one square instead of an interesting polygon, that would give you n squared. So in this, you would be plugging in n squared for the number of edges because you don't really have it. It is possible that maybe a specific on the instance it's much less, but you don't have that information. Okay, and then one last thing is maybe we have a couple of different running times. We can also look at the running time that you came up with in the homework. But one is just edge disjoint pass, which is in general fine here because everything's integral and it's a pretty small flow, but we have to estimate what lambda would be. And let me not use m because that already exists. So it would be number of edges times the size of the flow. We also did the shortest augmenting path, which would be number of edges squared times number of vertices. Okay. So say plugging in, for example, these two, we just said, okay, number of edges will be n squared. And then what's the best upper bound we can get for lambda, the size of the flow, in terms of this matching problem? N, okay. So that's one n cubed approach. The other, we said there's n squared edges, so this would be like n to the fifth or something. So you plug and play and you say, okay, n cubed is clearly much better than n to the fifth, so we should pick out Ford Fulkerson in particular. Let's see what else. I think, it's worthwhile at least stating, look, if there is at some level, there's, okay, so we have sort of an if and only if, right, between sort of our, I guess this one is maybe not so interesting. This is more relevant for like NP hard reductions. But, for a golf course solution where we pair up the holes and the starting points compared to, I guess, a matching of size n. Okay. So even just a little bit of lip service to say, look, if I'm able to match up all the holes and the starting points, that will give me a matching in the graph because I will never choose the same vertex twice, and there'll be n of them. And then likewise, if I have a matching of size n, that'll give me the matching. And that would probably be pretty boring sentences for this one, but it's good just to establish that. Yeah.
So for this solution, would we have to explain how we know that there's a line of sight?
Yeah, so I sort of skipped that. So for what it's worth, I may have consider putting this on the homework, but not on the exam because the line of sight thing, actually calculating it is a bit of pain. For our discussion, I just wanted to focus on identifying the matching. We can factor that in. So I guess there's probably clever. So I think in the solution, so in other words, this is probably more detailed than I would want to put in the exam because now you're worried about this thing that will take a page to write about. But I think maybe, okay, so what's,
It seemed like if you knew the order of the endpoints, you could then draw an edge between all the endpoints. And since we can determine that, if two lines intersect in constant time, we can just do a test to see if it intersects one of those edges before we draw ours.
Yeah, I think maybe this problem isn't perfect in the sense that it would be very convenient if the points were in order along the edge of the polygon. I probably would have added that if that were instruction on the homework. And then I think probably the relatively straightforward approach of for every potential circle and star, loop through the edges, and then just call this constant time thing to decide whether or not to put the edge would have been fine. And I think that if this were a homework and we were making a rubric, we would have, say, at least 8 out of 10 points focusing on just identifying the reduction to bipartite matching and checking that sound thing and making sure you're doing it constructively. I think that's the most important part. Yeah, I agree. Not perfect, but it's okay. All right, so so that okay, so does the solution make sense? It's bipartite matching where we only allow an edge if they can see each other, and then yeah. Again, I recommend just expanding this out to a sentence. If there's some kind of golf link matching thingy, then you get a matching in the graph because of this, and vice versa. It might be a boring sentence, but there may be a more complicated problem where it's more subtle. That's why it's a good habit, I think. Okay. Okay, so here again, I chose these problems that are horrible to project. I keep breathing into the mic. Okay, so let me try to explain this one. So I guess this problem is inspired by Scrabble. So so the idea is that you have a sequence of tiles. Right. Okay. So in Scrabble, we normally have a whole board. You have 7 letters in your hand, and you make a word, and then someone else goes makes a word, and then you get points depending on how much the letters are worth, plus some occasional double or triple word scores. But that's not entering the picture here. Okay. So this problem is sort of inspired by that, and so. Okay, so now in this problem, you're imagining you have a fixed sequence of tiles. Here would be an example of 20 tiles. I don't know if you can, let me zoom into the left column. So here you have a sequence of 20 tiles, and the idea is that you first draw 7 of them. Okay, so I guess that would be your first 7, and then you would try to find a word. Let's say that you have access to a quote-unquote dictionary where you can just submit it a string. It'll tell you if it's a word or not. Keep in mind there's only 7 letters, so you can do lots of brute force things over 7, and it'll still be constant time. You can try everything. And then you would play, I guess these 5, you could potentially play these 5 letters, which would use those 5, and then you would draw 5 more to get a full hand. 1, 2, 3, 4, 5. And then you would keep going. Okay, and the goal is to try to get as many points as possible. And so on and so forth. So of course, so the sequence is fixed ahead of time, and you know the whole sequence. Okay, so you can look at the full deck of cards, so to speak, and the letters have points, and I guess the rules here. This is not. We could do the other version of the rules, but the rules in this problem is that if you can't find a word, then the game ends. Okay, I guess an alternative version is if you can't find a word, you have to throw away the 7 tiles. You get a fresh 7. That also would be doable and maybe fun, but I'll stick to what's written. So the goal then is to sort of come up with the best sort of sequence of plays. Okay, so yeah, so you play some tiles, you get a new hand, you play some tiles, you get a new hand. And you can look as far as you want into the future. You're not doing any prediction problem. Okay. So we'll just focus, I think, maybe on part A is probably fine, and then if you want, you can do part B later since it's similar and you have some warm-up. Or if we have time, we can do part B. Okay, so part A, yeah, just try to figure out the maximum number of points for a fixed sequence of tiles. There are n tiles. Okay. Yeah.
I just had a question there to clarify for the last problem. If we drew that picture, could we do the picture and then just have a paragraph explaining it afterwards with our pseudocode and then what we would do with our runtime, or would a picture not really be sufficient for the exam?
I think that okay. So the question is, can I draw a picture? So I think the first order would be kind of not sufficient. There would be no place in a rubric for a picture. I suspect that if you had a picture, sitting in the margin and you had a crazy solution we couldn't understand or something, but we look at the picture and we're like, they seem to kind of be drawing lines that seem appropriate. We can maybe try to give back a little bit more or something to, if usually what happens if the solution is perfectly correct, that's very straightforward. When things are off, then we try to kind of make the most positive case for the problem. So in that sense, it might not hurt, but it's not probably not worth too much. Okay, do the instructions make sense for the Scrabble problem? Are they visible? Yeah. Yeah.
Earlier you said that passing the 7-letter sequence into a dictionary is O1. Like, exactly what is O1 in that situation?
Oh, well, I think, yes, let's say you have a subroutine that takes as input a string, their maximum size is 7, so a string of constant size, and we'll say it's a word or not. And I just give that to you as a subroutine. And remember, 7 is a constant, so you can do all combinations of all 7 letters and stuff like that, sort of in constant time.
Okay.
Right,
And I can
'cause-
try all possible combinations of any of those 7
7,
characters.
and it'll be whatever, 2 to the 2 to the 7 or something, but that's still a constant.
Thanks.
Yeah.
That's 5. It's like a great. I don't know. Yeah. You have to try. You have to keep trying. You have to compare your prime scores.
Professor, you said there's no double triple word for a single sequence we have. I mean, like for the cross-behavior, there could be only one word or can
Oh, that's because have you played the real Scrabble game before? Oh, okay. So in real Scrabble, there's like there's different things called double and triple. So if you haven't played real Scrabble, you can ignore the parentheses. You're allowed to use the same letter twice. You're allowed to. I mean, yeah. If you have two A's in your hand, you can use both of them. That's okay. Yeah. Just ignore the parentheses part if you haven't played Scrabble before.
Okay.
Yeah.
Thank you.
Yeah, like that's because I had one for scores, but there are certain and everyone like their distance from each other.
This is different. This is different. Okay. We went down, then up, up, down, and down, up.
Yeah.
Looking through all the words all one.
Yeah. Yeah. Because there's only 7 letters, so maybe it's 3 to the 7 or something. But
Return like a polynomial number of words.
oh no, just say you have
Factorial or something.
imagine you have a dictionary. So you just ask a word or ask a sequence of letters and says yes, it's a word. No, it's not. But you only have 7 letters in hand, so you can only even create like 3 to the or 7 factorial or something possible.
7
That's a constant.
Screw it.
No big deal for us.
Y'all are crazy. Okay.
No, 7 factorial, okay, what would that come out to? 42 times 5, 200 something times 4, 800 something times 3, 2,400 times 2, 4,800. It's less than 5,000.
Yeah, but if you do
Your
that,
computer's going to go that super fast.
okay, you're saying that you can do that. You can call that a constant and then multiply it by n, or multiply it by whatever.
You're more interested in the dependency on n. Yeah. Probably the fact that 7 factorial is hard for a person is why Scrabble is interesting.
Yeah.
But 5,000 is nothing for a computer, realistically. Like one instance of a video screen, I mean, has way more than 5,000 bits, one frame, right? So. Did you guys finish?
Stuck on an idea.
Okay. You guys want more time?
Yeah.
I think it's the best solution.
All right, show of hands. How many people have finished or are kind of ready to move on? Seems like most. Okay. Let me make a page. Okay, let me just copy a picture of tiles. Okay, so first of all, maybe at a high level approach, what if I were to classify problems as either change the input or identify the right subproblem? Who tried to do a change the input approach, and who tried to identify the right subproblem? Okay, good. Does anyone want to propose then a subproblem to try to break down? Doesn't even have to be right, even just a starting point for our discussion. Sure, yeah.
I have a function given the current n and the remaining tiles. Return the maximum score you can get.
Okay, so all right, so let's give it a name. Sometimes when I can't think of a good name, I just write best, because usually one way or another I want something that's the best. And so what was suggested, I'll leave this blank first, is that so maybe given, so you said the tiles that you have, so at some level it's some, we're trying to break the problem down into kind of moments, right? Where in a moment you make a decision and then you have something left to explain the rest. So in a particular moment, what's the full state? You have the tiles in your hand, so we'll figure out how to, given tiles, and I'll write in hand. I'll leave some white space so we can go back and make this more precise. and tiles that are left, the best, which I guess for us is max, possible score. Okay, so I think especially, so we haven't really done anything too formal yet, but at a high level, what have we done? We sort of described the state. We haven't been too precise yet, right? But at some level, that's all the information that's out there, the tiles you have in your hand, and what are the tiles that are left. Okay, and then we've also identified kind of what's the goal, what's the maximum score possible with these things. Okay, so that sort of describes the state and our goals. There's already a lot of, by the time you got to this point, you've already broken down the problem quite a bit. Okay, at some level, now it'll get more narrow and more precise. So, okay, so one reason, we need to be precise because A, we need to make an algorithm, and B, we need to understand how many subproblems we're generating and stuff like that. Okay, so let me start with so at some level, okay, we need to figure out each of these underlying proportions, a nice way to encode this, make this into bits, make this into numbers. Okay, so any proposals for maybe how to encode the tiles in hand? Yeah.
Would it be the 7 consecutive tiles minus the ones that you use to make a word?
Yes, okay. So definitely the beginning, it's kind of very easy. You can compactly describe, I have the first 7 tiles. But then as you pointed out, over the course of the game, you start spending some letters and you have other letters left, right? And then maybe these are the tiles that you actually have in your hand, the ones that are squared, right? So, how can I, which you've sort of alluded to. So now compactly then, what would be a reasonable encoding scheme? Just write down somehow that these are exactly the tiles I have in my hand. They could be very spread out, by the way, over the course of a game. Yeah. Yeah, at least unless we can think of something more clever, we could just write down the indices, the 3rd tile, the 5th tile, the 7th tile, and so forth. Okay, so there's another approach, but maybe I'll wait for that until the end. Maybe the tiles of index I1, I2 through I7. I guess, or is it possible to have less than 7? I think it's possible to have less than 7, or ij equals nil if less than j letters or something. Of course, not the most eloquent way to write it, but you get the idea. Okay, so given these tiles in hand, okay, and then we do want to compactly describe what are all the remaining tiles, right? So now I'm moving on to the next underlying proportion. How can I describe in a computational way, computer-friendly way, the set of tiles that are left in the sequence? Aren't in hand yet, they're sitting on the stack. Yeah. The number of, the number that's left? Yeah, you can use, say, there's 2 left, or you can say I'm at index n minus 1, or something like that. I'm going to say index n minus 1 because I find that a little easier, but either one would be fine. and tiles starting from index k, remaining the best or maximum possible score. Okay, so I think this will concisely describe, handwriting's not great, but this will concisely describe exactly the state of the game right now when you're making your decision. Okay. All right, so then our full set of indices, it looks like our subproblems are ultimately parameterized by 8 indices. The first 7 describe the letters in your hand. The last one describes sort of the index at the top of the stack. Okay, which is again really great because you've taken this sort of very messy, long story of a problem, and you've already identified sort of n to the 8 or something subproblems to break it down into. Yeah, it's a little messy, but it's better than exponential. Okay, and things are starting to clarify. Okay, so now if I wanted to implement and keep in mind, all I want to do at this point, insofar as we're confident in our sentence, is just to implement that sentence. At some level, I've abstracted out a lot of the details. So, okay, so best I1, I2, I7, okay. Yeah, this problem's a little messy, so maybe we'll give a somewhat high level code. It's okay to say, oh, try all of this or something, and sort of making 7 loops explicitly. Okay. All right. So where to start? Like one thing is we can knock off some basic base cases. So this is still structurally important. For this problem, what might be a base case? How to describe a base case, something where the recursion ends. Yeah. Yeah, okay, so the rule was if I can't make any more letters, the game ends. So I'll just describe it at a high level. So if no words can be made from the 7, I guess, or less letters indexed by I1 through I7, then return 0. The game ends. You can't make a word. You're done. Okay. All right. So now in the interesting case, we just want to try some stuff and then identify the right subproblem to solve the rest of the problem optimally. Okay. So this is the more interesting case. What might we do, at least at a high level? I know writing out all the details is kind of messy for this. At a high level, how might I proceed stepwise? Okay, 1 more minute and see if I can get. Okay, well, what did you have in mind?
Maximum word, all the unavailable words in your hand. Maximum best your hand minus the word plus the next draw.
Yeah, okay, so let's see. Uh, I, all right, I'll cheat a little and I'll be clumsy. This is too messy for me to want to put on a test, of course. But it's a fun problem. Okay, so I'm going to try to return to maximum over sort of all words. How would I write this? Okay. W out of our letters. Oh, let me first write it down at a high level and see if I can think of a nice, concise way. Or overall words, W out of our letters, sort of, what is it? The sum over, I guess I would sum up the values of the letters. Okay, so maybe what should we do? We should, the point is we should get the value of the word plus the best of some set of new letters, and I should subtract out okay, I might run out of letters, so this is very messy. So this isn't a very good solution, but that's okay. Let me first try to understand what's going on. Okay, where J1, JK are the indices of the new hand after using the letters in W or something. Okay, so it's not, yeah, sorry? Oh, it should be 7. I'm not sure why. Okay, I chose 2 examples today that are a bit messy, but that's hopefully they're fun anyway. Okay, so okay, not a great solution. Okay, so but let me first at least make sure we're on the same page at a high level. We're just going to try all possible words that can be made out of the 7 or less letters you have. So maybe I7 or I6 is set to null if you only have 5 letters left or something. I want to point out that, okay, I sort of swept a big loop under the rug, but that loop has constant size. That's one thing important to point out because however many combinations and permutations and really different strings you can make out of 7 letters is still only, I don't even know what the actual number is, 7 to, it's more than 7 factorial because you can leave out some letters. So I guess it's, anyway, it would be 7 factorial plus 7 choose 6 times 6 factorial. It's a big number, but it's a constant. Okay, in fact, I was estimating with some of the students, 7 factorial itself is probably only like 5,000 or something like that, which is much less than the number of bits in one frame on YouTube or something. So it's not even a big deal. So we'll loop over everything. We'll try all the words. And I guess here I'm treating W as the set of indices into words, okay? And so I'm getting the score of the word by summing up the indices in the word and getting the value. And then I'm updating the subproblem, okay? And somewhat lazily, I wrote this sentence saying, oh, we'll just figure out the appropriate indices in the obvious way. I updated the number of tiles that are left. Oh, I guess this was, I think I did this wrong. Based on ours, so K is supposed to be the first letter that's left, so I should have wrote, maybe I'll write it this way. I'll just write I'll just write this where okay, so I take, if I spend 5 letters, I take 5 letters, I advance 5 letters, and then maybe I'll be lazy and I'll say K bigger than N means no letters left or something. Somewhere we should encode that or update it to make sure it stops at N or something. Okay, so get the score. We update the subproblem. Okay. Now, okay, we only have a few minutes left. I want to at least mention why this or let me first ask, what is the running time of this algorithm? If I ran the whole dynamic programming, and I'll address correctness in a moment. So what is the running time? This seems like a messy thing. I mean, I didn't even really figure out a clean way to express the whole thing correctly. Okay, but still, you should be able to eyeball the running time of this approach. There's n letters in the original sequence. Yeah.
Would it be somewhere around n squared times that constant combination of all 7 letters?
Okay, so why n squared? That's true. It's definitely similar, but it's going to be bigger than n squared, and there'll be a more direct way to see this than by similarity. Yeah.
I think if all letters, all the same letters have the same score, then you would just have like n. But if all the letters have different scores, then you will have like n8.
Yeah. So let's just do the version that we have here, which we were writing down the indices. So that would be okay. So how many subproblems do we have? Yeah. It is. It is. So how many subproblems are there? Yeah, there's 8 inputs, or 8 interesting inputs, I1 through I7 and K, and there's basically up to n choices, or it could be nil or something, so maybe n plus 1. But there's roughly n choices for each input, and there's 8 choices of input. Okay, so we have n to the 8 subproblems. Yeah, it's kind of crazy, but it's a polynomial. Okay, you should expect something crazy. The problem is crazy. Okay, and of course I didn't write all details, but roughly how long does it take to solve a subproblem? Yeah, O1, because we're doing some crazy loop, but ultimately it's over kind of combinations of size 7 or less. Okay, so your constant here might be 10,000 or something, but that's okay. Your running time will be like 10,000 times n to the 8, and nobody will mention the 10,000. Okay, so just by kind of at a high level, recognizing based on our sentences how many subproblems I constructed, I realized that there's n to the 8 subproblems, each of which takes sort of a big constant, but ultimately constant time, and you get an n to the 8 running time. Okay, it's messy, but you zoom out, the conclusion is clear. That's what's nice. Okay, and I think let me briefly mention why it's correct. I think this is all sort of you guys sort of already feel and appreciate this, but I just want to make it explicit. Ultimately we're relying on induction. So I'm assuming that for any subproblem, okay, for any subproblem, I'm going to solve the problem correctly by induction. Okay. Now the base case where there is no subproblem, it's very easy to see. Oh, if there's no words left, then the only thing you can do 0, and I feel very confident about this. And in a general case, I'm trying to solve how to solve, do something right now. And I assume I can deal with kind of less tiles left optimally, right? So this way I say, okay, there's some optimum solution out there. It must form some word. I don't know which word. So I'm basically guessing and trying all possible words that the optimum solution does right now. Okay. And then to argue that I do the rest optimally, I'm saying, oh, by induction, sort of on the stages of the game, so to speak, treat it as sort of a directed acyclic graph. I assume that my subcall is going to do things optimally. Okay, so when I'm doing recursion, I'm assuming that the recursive part does things perfectly. You are using induction. Okay, whether, maybe that feels automatic and stuff, but that's ultimately the principle by which your algorithm is correct, even though otherwise it's a messy, complicated, who knows what's going on kind of problem. Okay, but we sort of abstracted out a lot of stuff. And just by identifying subproblems, we take this big messy thing and turn it into a couple steps that are a little bit easier to understand. Okay? All right, that's good. So the other problem was fun one. It's just an induction problem, but we're out of time. So I'll leave it up here as you guys shuffle out. I'm happy to answer more questions.